In 1881, a physicist named Albert Michelson found a way to measure extremely small differences in the speed of light. This is precisely what we need to verify the Galilean transformation for light. His basic idea revolved around light interference patterns. For example, if we combine two waves that are in sync with each other, they reinforce the output wave. As we shift one of the input waves, we see the output deviate from the maximum reinforcement. As we reach 1/2 of a wavelength out of sync, we get total destructive interference. The waves, in effect, cancel each other out. If we keep going, we move back into complete constructive interference as we reach one full wavelength. What Michelson did was to leverage this light interference behavior in what we now call an interferometer. Here's one from the MIT physics lab. A light source shines light into the interferometer where it is split and reconstructed using mirrors. The reconstructed light shows up on a screen. The bright lines indicate areas of constructive wave interference, and the darker lines indicate areas of destructive wave interference. Moving the mirror changes the position at which the light constructively and destructively interferes. Here's how the light flows through the apparatus. First, the incoming light source is split into two by a partially reflecting mirror. These two beams then reflect off of mirrors and recombine at the splitting point. If the distances traveled are exactly equal, they will be in sync when they recombine. This produces the maximum constructive interference. The main fringe has been marked with tape to help keep track of any shifting. If we move one of the mirrors by 1/4 of a wavelength, that wave will have traveled 1/2 of a wavelength less distance than the other one. This produces the maximum destructive interference. You can see the shift in the fringes from the bright to the dark. As we continue to shorten the wave to the point that it travels one whole wavelength less than the other one, we return to being in sync and get back to maximum constructive interference. The fringe pattern has now shifted one full fringe, producing a pattern just like the one we started with. As we continue to shorten the path for the split wave, we can count the number of fringe shifts. In our experiment, we shortened the wave by 65 micrometers and produced 10 fringe shifts. A simple division gives us the wavelength. So knowing the distance and counting the shifts gives us the wavelength. But as we'll see shortly, the important thing for us to note is that knowing the wavelength and counting the shifts gives us the distance. The split wave was shortened.